So any questions from previous topics? Yeah, Bharti, what about assumptions of linear regression? We spent almost half an hour discussing assumptions of linear regression. So where specifically do you have a doubt? So you need to tell me specifically where you have a doubt. You cannot ask a very broad question like that. Okay, because if I start that, it will take me half an hour. So for that, you can always go to the recordings and see. Okay. Yeah, the linear relationship between independent and dependent variables. So, what is the doubt here? No, it is not same. It is very different. So, linear relationship means, let me give you an example. So, let's say you have price of house. Okay, you have price of house, which is your dependent variable, and let's say you have total square feet or total area of the house. You have that as your independent variable. Now, both these you can plot, you can draw a scatter plot for them. So you plot your y here, you plot your x here. So you will have some points like this. So this looks like a linear relationship, right? Because if you draw a line, it will fit something like this. So this is a linear relationship. This is one of the assumptions that your dependent variable and independent variable should have a linear relationship. This is the first assumption that you talked about. Homoscedasticity is something different. Homoscedasticity is that your residuals. So what are residuals? Residuals are the errors that you will get. So when you plot these points, you will get some errors, right? So when you plot those errors, so when you draw the residual or the error and the predicted values, this is the predicted values, okay? So you know your predicted values, you can know the errors. So when you draw a plot between these, homoscedasticity says that it should have a constant variance, which means this distribution should be almost similar. So this has a constant variance. Okay. And the other one is that there should not be any pattern. So it should not be something like this. The same plot here, it should not be something like this. So this is not even constant variance, and there is a pattern. There should not be any pattern also. So see, there is a pattern here. It looks like a funnel. The variance here is less and it has increased here. Plus there is a pattern also. So this is heteroscedasticity. So these two conditions should not be there. That is the other one which you mentioned. Okay. So both are entirely different assumptions. I had shared an additional video. I had shared an additional case study. I'm not sure if you guys have watched it yet. So this is the case study which I'm talking about. I had shared this additional video. This one. This is also from a live class which I took earlier. So do watch this, okay? This explains about a detailed case study. So that will help you understand. Okay, this is a 3-hour video. So 3 hour 40 minutes. It's a very long video, but this will talk about a case study. So first it will describe the problem statement. Okay. So first I will talk about the problem statement in this case study. Then I will solve that problem using the data that is given. So even the data is okay. I forgot to share the data. I will share the data for used in this video also. Yeah, good, Naresh. So try to complete it and then try to replicate it in Python yourself. Okay, try to do that in Python without looking at the codes. I will share the codes and the data, but try to do it yourself without looking at it. Okay, so this is like a case study on linear regression. Okay, where you have a problem statement and you will try to solve that problem statement using linear regression. Okay, any other questions, guys? Do you have any other questions? Okay, so let us move ahead then. Okay, so today we will talk about logistic regression. We will move to a new topic today, which is logistic regression. So this will be a totally new topic. So if you remember, guys, in supervised learning, so what is supervised learning? Supervised learning is where you have a dependent variable, okay, where you try to find this function f. This is what we try to find. This is supervised learning. If you remember, supervised learning is divided into two parts. One is called regression and one is called classification. Okay, so in case of regression, your y is continuous. In case of classification, your y is categorical. Okay, so we have seen one algorithm for regression. So we have seen one linear regression. Okay, today we will talk about, or for the next maybe couple of classes, we will talk about logistic regression. Okay, this is where your y will be categorical. It will not be continuous values. It will not be price of a house. It can be if a house is luxury or not, so ones and zeros. So it can be binary or it can be more than one category, let's say 0, 1 or 2, where 0 might stand for, let's say, small, let's say this is medium and this is large. So you're trying to predict something which can be either of the three, either small, medium or large, or 0 and 1, yes or no, for example. So this is what you will try to predict in case of logistic regression. Okay, we will first start with a very simple case. We will start with binary classification. Later we will go to more than two classes, but first we will start with binary classification, where our y will take only two values, which is 0 and 1. 0 means no, 1 means yes. Okay, so examples can be a bank would want to know whether to give loans or not. Okay, give loans is 1, not means 0. This is one example. The other example is, let's say, whether a customer will churn or not. Customer churn. So 1 or 0. 1 means yes, he will churn, he or she will churn. No means 0 means no, they will not churn. So if a telecom company, let's say Airtel, if Airtel gets to know in advance which of the customers are planning on moving to a different telecom operator, they can give some offer and they can try to retain the customers. So this is where churn models are very helpful. Even all companies are trying to build employee churn models. So employee churn means which of their employees is planning to quit the companies. Okay, so that if they know in advance if some employee is trying to quit, and if they really want to retain that employee, they can give him something, maybe an on-site offer, or they can give him a raise in salary, whatever. So this is where these are few examples of classification models or logistic regression. In particular, we will start with this. So there will be several other algorithms also we will see later, which can also be used for same cases. So for example, whatever case studies we did with linear regression, the same can be done using some other algorithms also. We will see those later. Okay. So first we have covered linear regression. Now we will cover logistic regression in details, and then we will move to the other algorithms. Okay. Any questions on this? Another example of classification is, for example, Facebook. When they tag you, Facebook, if you know guys, if you have noticed, if you upload a photograph on Facebook, it will automatically tag all the person in that photograph. So that is also a classification case which Facebook does. It tries to identify your image based on the repository of images Facebook has, and it will try to tag that person. So that is also a classification case where you have thousands of classes, thousands of categories, not just ones and zeros, but thousands. Any questions so far before I dive into the details of logistic regression? Because the face may belong to anybody on Facebook, right? Let's say you upload a photograph on Facebook. So the people in that photograph can be anyone from your friend list. So if you have 2000 friends on Facebook, that face may belong to any of those 2000 friends. So Facebook will run a classification algorithm which will tell it which friend has the highest probability, or the photograph, to which friend will it belong, how likely is it to belong to one particular person, and accordingly it will do yes, match or not match. So if you have, so let's say you have 500 friends, so 1 2 till 500, and you upload a photograph, there are two people in that photograph, let's say. Okay, and there's you also, let's say this is you and there are two other people in that photograph. So Facebook will start matching this one, and so on. It will start matching all the 500. And finally, the algorithms of Facebook will tell it that person number 5 has the highest probability. So this person probably is person number 5. He resembles most with person number 5, because Facebook will have many images of this person also. This person will also have a Facebook account, and definitely Facebook will have many images of this person also. So Facebook can easily do a matching. The algorithms can easily tell Facebook that, okay, with respect to this person, the algorithm will give the highest probability. And so Facebook will automatically tag this person as person number 5. So this is also a classification algorithm. Okay, of course, it's not so easy. The algorithm should be very robust to detect 1 out of 500 or thousands of people. But that's why it is Facebook, right? Okay, is that clear, Anupama? Okay. So before we dive into the details of logistic regression, let us first see how would we evaluate a logistic regression model. Okay, so if you remember in linear regression or for any regression model, what did we see? How did we evaluate the model? Tell me, guys. How did you evaluate a linear regression model? Tell me. What parameters did you use to evaluate a linear regression model, whether it was performing good or not? No, I'm asking what parameters. Beta 1 and beta naught, Anupama, those are not parameters that you use to evaluate. You cannot look at beta naught and beta 1 and say that your model is good. Okay? Bharti, you cannot look at the test data and say that your model is good. Yes, so Sinu is right. We look at the errors, right? We look at, Arpita is also right. We look at error and accuracy parameters and then we decide whether the model is good or not. I'm not asking how do you build a model, how do you find beta knots. I'm asking how do you evaluate a model. Okay, so two ways. One is looking at the error parameters, which we saw where SSE, sum of squared errors, mean absolute percentage errors, root mean squared errors, or we also looked at R square. If you guys remember, we looked at R square, adjusted R square. These are accuracy parameters, these are error parameters. So we looked at these parameters and we tried to evaluate our linear regression model. Now, do you think these parameters will work in case of classification? What do you think? If if they don't work, why wouldn't they work? Or if they work, why would they work? Do you think we can use these parameters to evaluate a classification algorithm also? What do you think? Okay, Amit says no, we cannot use these parameters to evaluate a classification algorithm. Okay, Amit, then why do you think we cannot use these? Is that Arpita? Okay, so yes, you guys are right. So remember in regression, what did we see? Let's say our y was price of a house. Okay, our y was price of a house. So let's say price is 100. The actual price of a house is 100 and you have predicted, let's say 120. Then you can easily find your error by doing actual minus predicted, so which is 20, right? But in case of classification, you will just have yes or no. Okay, let's say 1 or 0. You will have 1 or 0. So your actual value is yes or no, and what you predict will also be yes or no. You cannot predict something else because you know that your answer is either yes or no. So what you will predict is also either yes or no, right, guys? What you will predict will also be a yes and no. It cannot be something else. You cannot predict something else, a third number. You will only predict 1 and 0. You will not predict that third number, let's say 3. It wouldn't make sense because you know that your output is only 1 and 0. So you will also predict 1 and 0. Now here also you can make error, of course, but what error you will make? If it is a actual, and let's say this is your predicted, the error that you can make here is if it is actually a yes, you predict a no. This is one error that you can make. And the other error is if it is actually a no, but you predicted a yes. So these two kinds of errors you can make. Is there any other error you will make apart from these two? So actually it was a 1, but you predicted a 0. And actually it was a 0, but you predicted a 1. Is there any other error apart from these two you can make? No, there is no other error. So these are the only two cases where you can go wrong. Okay. So to evaluate, and where can you go correct. So let's also calculate the accuracy. So just like we discussed in case of regression, there are two ways of looking at a model. Either you can look at how good the model is or how bad the model is. So when you look at the error, you are being pessimistic and you are looking at how bad the model is. When you look at accuracy, you are being optimist and you are looking at how good the model is. So you can be good in cases where actually it is a yes and you also predicted a yes. So actually a 1 and you predicted a 1, and actually it is a no and you also predicted a no. So 0 for 0. So these are the two cases of accuracy, and these are the two cases of errors that you can have. Okay, there is no other possible case here. Either of these four will happen. There is no other way you can actually have a scenario. Okay, now this is true not just for logistic regression but for any classification algorithm. Okay, this is true for any classification algorithm. Now how do we get the predicted values that we decide based on different algorithms? You can do logistic regression for it, you can do a decision tree for it, you can do a support vector machine for it, or any other algorithm you can use to predict this no and yes. But after getting this no or yes, the way you evaluate is the same. Okay, you will use the same, these two conditions to evaluate the error. You will use the same two scenarios to evaluate the accuracy. Okay, is that clear, guys? So let us see how do we evaluate in details. Okay, so the way to do that is we create a matrix. We create a matrix which will help us study these two very easily. Okay, because studying these two like this separately will be a little difficult. So what we do, we create a matrix. Okay, we write the actual values on the left hand side. Okay, and we write the predicted values on the right hand side. Okay, what are the actual values we have? The actual values we have is yes or no, right? There is no other actual value that we have. We either have a yes or we either have a no. Similarly, what predicted values do we have? We either have a yes or we have a no. There is no other value that we can have. So I have written the actual values here and I have written the predicted values here. Now what I will do is I will create a table like this. Okay, I will create a table like this. Okay, and then what I will do is I will count the number of cases where actually it was a yes and I predicted a yes, and I will write that number here. Okay, I'll write that number here. Similarly, I will count all the places where actually it was a yes but I predicted a no, and I will write that number here. Okay, and similarly for this, actually a no and I predicted a no, and actually a no but I predicted a yes. Okay, so which of these four numbers do you think are errors? Which of these four boxes do you think will be errors? Tell me. This one, is it good or is this bad? Is this an error or is this something good? This first box. Yeah, this is good, right? Because it is actually a yes and you predicted a yes. So this is something good. This one, what about this one? Yes, that is bad. Because actually it was a yes, but you predicted a no. So I'll give it a cross here. Similarly, the third one is also bad because actually it was no. All others are bad. Bharti, what about this one? Is this bad? Because actually it was a no and you predicted a no. So this is also good. So you will have two good and you will have two bad. That's what we saw here, right? We had two good and we had two bad. Okay, so the same. These are the same that I have written here. Here I have written that in form of a table, and here I have written it separately as a text. Okay, so this is what we have. We have two bad quantities here and we have two good quantities here. Okay, now how do we calculate the accuracy? To calculate the accuracy, we just take the sum of these two. Okay, that gives us the accuracy. And similarly, to calculate the error, we take the sum of these two. So that is how you calculate the accuracy and the error in case of a classification algorithm. Okay, let's see this with an example. Let us actually do this with an example. So let me give you a hypothetical case. Let's say where you have actual value and you have predicted value. So don't worry about how these predicted values came, because we are yet to go into logistic regression. So right now just assume that we somehow got the predicted value. Okay, so can you tell me what number should I write here, guys? What number should be written here? So I'm writing the row numbers here. I have total 8 rows. Okay, out of these 8 rows, for how many rows is it actually a yes, and I have predicted a yes also? That is what you have to give me. Okay, Hima is saying 2, others are saying 3. So for how many of these rows was it actually a yes and you predicted a yes? Okay, this is 1. Row 1 and 3. 3 I have predicted a 0. Bharti, I have not predicted a 1 for 3. I have predicted a 0. Maybe this one. So only row number 1 and row number 8. Right? So 2 rows. So I'll write the number 2 here. Okay. Similarly, now this one, what number should I write here? Actually a yes, but I have written a no. 2. Okay, actually a yes means 1 and I have predicted no, so this is 1. And what else? This one. Right? So 3 and 7. Right? Right, guys? So here also I will write 2. Okay. Now let's move to the next one. How many of them are actually a no, but you have predicted a yes? Actually a no, but you have predicted a yes. So this one, this one, right? So once again 2. And this one, do I need to actually count this? Because I have, out of 8 I have written 6 already. So I can just do 8 minus 6, which is again 2. So I don't need to count, because only these two remain. One is this and one is this. So obviously those two will come here. Okay, there will be no intersection. So this is how it looks like. So it luckily happened to be 2 2 everywhere, but it need not be. Okay, it need not be like this. It can be any number. It can be 0 also somewhere. So this is what you have. Okay, now as we discussed, these two are good quantities for us, right? The higher these numbers, the higher these two diagonal numbers, the better for us. And similarly, the smaller these two numbers, the better for us. So how do we calculate the accuracy? So we have a parameter called accuracy. Okay, in all classification models we have a parameter called accuracy, where we just add these two numbers. Okay, so I'll add 2 plus 2, which is 4, divided by total. Okay, so 4 divided by 8, which is 50%. So the accuracy is 50%. That means out of total 8 rows, 4 rows you have predicted correctly. Right guys, this is what it means. That out of 8 rows, 4 rows you have predicted correctly. These 4 rows, this one and this one. Okay. Similarly, you can calculate the error also. So the error will be this 2 and this 2 divided by total. So once again 2 plus 2 divided by total, which is again 4 by 8, which is again 50%. Okay. So this means 50% of the rows, or 4 out of 8 rows, you are not able to predict correctly. Okay. 50 out of 100 rows you are not able to predict correctly. Yes, Bharti, it is similar. We will come to chi-square test later. Okay. So this is how you calculate error. So this is your accuracy where you add these two numbers, and this is your error where you add these other two numbers. In this case, both happens to be the same. And you can also calculate the error by 1 minus accuracy, because the total should be 100%, right? So the total should be 100%. So error can also be calculated by 1 minus the accuracy. So 1 minus 50% is again 50%. Is this clear, guys? Is this clear? Any doubts on this? That your stakeholders will decide whether 50% accuracy is good or not. That your stakeholders will decide. Okay. We will come to that later, Shinoj. When we do some examples, you'll understand. So right now, just understand how do we evaluate. Later we will see is this good or is this bad. But right now, just understand how do you calculate the accuracy. So this is what we do to calculate the accuracy. Okay, we prepare this table, and from this table we find out the accuracy or the error parameter. Now this table has a name to it. This table is called confusion matrix, or confusion table, or it is also known as contingency table. Okay, but more popularly known as confusion matrix. You will see why it is given the name confusion. So far it looked pretty simple, but right now what I will tell you, that will add a slight confusion there. Not a confusion, I'll give you a cheat code to remember, but it can get very confusing for some people. But we will see why it is called confusion matrix. Okay, right now, so far it is very simple. But right now let us see. Now these numbers that you see here, they have some particular names. Okay, these boxes have particular names here, because otherwise how will you identify which two is this? You will not know which of these two is this. So we have some particular names for these. So let us look at those names now. So let me write that again, the table again. This is your predicted, this is your actual, yes, no, yes, no. Okay. So as I said before, each of these boxes will have some names. Okay. Each of the names has two words. Each of the names has two words. I'll give you a cheat code which will help you to remember the words. Okay. So each has two words. One is the first word and one is the second word. Okay. The first word is always either true or false. Okay. And the second word is either positive or negative. The first word in all of these will always be either true or false, and the second word will always be either positive or negative. Okay. Now, how do we know which one is which? So first, let us talk about the second word. Then we will come to the first word. So this is the cheat code, which you will not see anywhere. So if your predicted value is yes, that means your second word will be positive. Okay, if your predicted value is yes, the second word will be positive. If your predicted value is no, the second word is negative. Is that clear? If the predicted value is yes, that means the second word is positive. If the predicted value is no, that means the second word is negative. So now can you tell me the second word for all of these? What is the second word for this one? Yes, guys. What is the second word for this? Positive. Yes. So let me write positive. Okay, I'll write P for positive because it is a yes. Similarly, the second word for this one, once again positive because it falls in the same column. Why negative, Hima? This is in the same column. Don't look at the actual value, look at the predicted value. So the column name you will look at, not the row name. Okay, you will look at the column name because I have written predicted value, not the actual value. You will not look at the actual value, look at the predicted value, so the column. Similarly here it is no, so it will be negative, the second word, and it will be negative because for both of this the predicted value is negative. Okay, so this is how you get the second word. It is easy, you will remember this much. So this you will have to remember. Okay, now the first word is very easy. Getting the first word is very easy. If actual is equal to predicted, then you write true, else false. Simple. If both actual and predicted are the same, then you write true, otherwise you write false. So here both actual and predicted are same, right? So you will write true. So that means this is called true positive. Okay. Here both are different because your actual is yes and you have predicted no, so you will write false. Similarly, here also you will write false because actual is no and you predicted yes. And here you will write true. So these are the four words that we have to remember. So you will have to remember these four words. You can use this cheat code to remember if you want. So however you can remember. This is a cheat code which I have formed myself. This is how I remember. If you feel this is helping you, you can remember using this cheat code, or you can create some cheat code of your own if you want to remember. But these four names you will have to remember. Okay, this is called true positive, where actually it was positive and you predicted a positive. This is called false negative, where actually it was a positive but you predicted a negative. So it is a false negative because you predicted a negative but actually it was false. Okay, similarly false positive and true negative. So these are the four numbers that we have. So now if I have to write the same formula again, accuracy, what is the formula for accuracy, guys? Tell me. What should I write? What are those two numbers that I will add? Which two numbers will I add here? Yes, I will add true positive plus true negative, right? These two numbers, these two are good for me, right? These two are good numbers divided by total. Okay. Similarly, the error will be false positive plus false negative divided by total. So remember, in accuracy we are adding the true quantities. So this is true and this is true. In error we are adding false ones, false and false. Both false we are adding in error and both true we are adding in accuracy. Okay, this you can write is equal to 1 minus accuracy, or you can just write accuracy plus error is equal to 100%, which obviously should be. Using this also you can calculate one of them if you know one. If you know accuracy, you can calculate the error using this, or if you know the error, you can calculate the accuracy also by using 1 minus the error. Okay, so this is the confusion matrix. Any doubts on this? guys, any doubts on this? Okay, now these are plain accuracy and plain error parameters, okay, which have been created using the confusion matrix. Now, depending on the business scenario, you might want different kind. There are several other parameters also that we will see now, and depending on the business case, you will give importance to one of the parameters over the other. So what are the good parameters in this? What are the good parameters? We have seen that true positive and true negative, these are the two good parameters we have seen, right? Now, depending on the business scenario, we will try to give more importance to one of them, and accordingly we have some other parameters also. Okay, now let us see one business scenario where you will try to give more importance to one of these parameters. Because if you see accuracy, look at the value of accuracy. It gives equal importance to both of them. It is adding both the numbers. That means it is giving equal importance to both true positive and true negative. It doesn't matter which number is higher. As long as both are being added up, that means they are giving equal importance. So it is 1 into true positive plus 1 into true negative. That means both have a weight of 1. They are giving equal importance to true positive and true negative. Okay, but sometimes your business scenario will be such that you will have to give more importance to one of them. Okay, let us see one such business scenario. So let us say you are a hospital, you are a cancer hospital, and you are trying to identify cancer in patients. So the patients which visit your hospital, you are trying to do a check, a test on them, and you are trying to identify whether the patients have cancer or not. Okay, so let me write the business scenario, which is identifying cancer patients. Okay, so let me write here actual values. So actual yes means actually this patient has cancer. Actual no means this patient does not have cancer. Similarly, let me write predicted yes. That means the hospital or you predicted yes for this patient, and no means you predicted no for this patient. So once again, I'll have a confusion matrix. So let me draw that. Now, is this number good for you or not? Is this box good or not? Where the patient has cancer and you predicted cancer. So this is definitely good, right? And what is this called? What is the name of this? What are the two words? Yes, true positive. It is a yes, so the second word is positive, and both are matching, so it is true. True positive, and it is good for us. Okay. Similarly, what is this? What is the name for this? Yeah, it is no means it is negative and false negative. Similarly, this one is false positive and this one is true negative. Okay. Now let us look at these two error parameters. First, let us look at the false negative and let us look at the false positive. Now, which of these two do you think is bad or is very bad? Obviously, both are bad because both are causing error. So your error is Fn plus Fp divided by total. So both are bad. But which one is more bad? Which one is more bad? Is false positive more bad or is false negative more bad? So understand from the business scenario. Look at the problem. You are trying to identify cancer patients. Which of these two will be bad? Okay, Vikram says false positive. Others are saying false negative. Okay, half of them are saying false positive, false negative. Okay, let us look at this first. Let us look at this first. Here, the patient has cancer, but the hospital says that the patient does not have cancer. So what will be the extreme case here? The patient has cancer, but the hospital says he does not have cancer. So what will be the worst case scenario in this case? The worst case scenario will be that probably the patient will never know the truth, and by the time he knows the truth, he will be in the last stages. So it will be irreversible, right, guys? That will be the worst case scenario. He will die without treatment. He will definitely get to know, but by then it will be too late, and nothing can be done about it. So the patient will die, right? And let us look at the other case. In this other case, what would happen? The patient does not have cancer, but the hospital says that the patient has cancer. So what would happen in this case? What is the worst case scenario? The worst case scenario is probably the patient will go through a diagnosis, and at some point, after spending maybe lakhs of rupees, he or she will realize that he does not have cancer. Right? At some point, he will get to know that he does not have cancer. So this is like being extra cautious. Even before you have, let's say, cold, you take a cold medicine. So he might have some side effects, but at least he will not die. Right? Do you agree when I say at least he will not die? Maybe he will go through a chemotherapy, he will lose all his hair, he will spend lakhs of rupees, but at least he will not die in this case, right? So obviously this first one is more worse. This first one is worse. Okay, so this is a worse case of error compared to this. Okay, this is worse. This is worse because this will result in the death of the patient. This will not result in death of the patient. Yeah, he might go for a second opinion also. So did all of you understand why false negative in this case will be worse than false positive? And again, this is with respect to this business case. In some other business case, false negative need not be worse. Okay, this is with respect to business scenario. So in this business scenario, false negative is worse. Okay, it changes based on the scenario. So do you agree that in this case, false negative will be worse? Okay. Arpita, this is the best example to understand why false negative is worse. Okay, because here in one case you have death, and in other case you have just some money being spent. So obviously nothing is worse than death, right? So that is why this is the best example or the extreme example to understand. All other examples that I'll give you will not be so. It will not be so apparent. Okay. So, so since the importance changes from case to case basis, if you were evaluating, if you just measure error, if you just measure error, what will error measure? Error will just do false negative plus false positive divided by total. So even if your this quantity is high or this quantity is high, you will not be able to measure that because error will add both of it. Okay, so this error, you will never be able to know whether this one is more or this one is more because you have added both of them. So you will just get the sum of it. So which of these is more, you will never know. What you will want is this one to be less. You will want this quantity to be less, and this, even if this is high, it is okay. Even if this is slightly high, you are okay, but this quantity should be very less. But if you measure error, you will never know which quantity is less and which is more because all you get is the sum. So that is why we have a few other parameters also. From the confusion matrix, we have a few other parameters also apart from accuracy and error. We have a few other parameters. So let us see those other parameters now. Okay, so we have another parameter called sensitivity. Okay, so what is sensitivity? This is also known as recall. Okay, this is also known as true positive rate. Okay, sensitivity or recall or true positive rate. Now what is the formula for this? This is true positive divided by true positive plus false negative. This is the formula for sensitivity. Let me write it here so that you have all the formulas at the same place. Let me write it. Maybe I should write it here. 1 second. So sensitivity or recall or true positive rate, this is equal to true positive divided by true positive plus false negative. Okay, so this one, if you see, it is just the row total. This is the row total. So TP plus FN, this one, these two quantity. Okay, so what does this measure? This measures out of the total. What is the denominator here? Can somebody tell me what is the denominator here? What is the denominator here? Yes, what is the first row? What is the first row? Can you give one name to the first row? Yes, all the actual, yes, exactly. All actual, yes. And what is the numerator? Now, can you tell me the numerator? What is it? What does true positive mean? What does the numerator means now? Yes. So what does this measure then? If I ask you the interpretation of this, what does this measure? So true positive is basically all the ones that you identified, right? True positive is nothing but all the ones that you identified, right? Because actually they were one and you also predicted a one. So can I write sensitivity or recall or true positive rate as out of all actual ones, how many ones did the model catch? Can I write this? Is this correct? Out of all actual ones, so denominator is all the actual one and numerator is how many ones did the model catch or did you identify. So this is the interpretation of sensitivity, or you can write it in another way. How many ones did you catch out of all actual ones? Okay, catch or maybe predict. Okay, out of all actual ones, how many ones did the model predict? So this is what sensitivity or recall means. This is the interpretation for sensitivity or recall. Do you follow, guys? It is very important to understand the interpretation of sensitivity or recall. Formulas you can remember or you can Google and you can get, but it is very important to remember, understand the interpretation, because only if you understand the interpretation you will give importance to these parameters based on your business scenario. Okay, so let me repeat. Sensitivity or recall, what does it measure? It gives more importance to true positive. Okay, so true positive in the sense, a patient who has cancer, identifying that patient is more important than identifying a person who does not have cancer. So in the accuracy parameter also we have two quantity, one is true positive and one is true negative. This one measures whether you are correctly identifying a cancer patient or not, and this one measures whether you are saying no to a patient who does not have cancer. Both have different meanings. Okay, so think about this, guys. Both have different meanings. You will have to put uh, you'll have to think this yourself. I cannot stuff this in your mind, but you'll have to think it yourself. True positive means somebody who has cancer and you say that he or she has cancer. Okay, this is different compared to somebody who does not have cancer and you say that he or she does not have cancer. These two are two different things. Okay, these two are two different things, and this one is more important for the reasons that we discussed. Because if this number is poor for you, that means you will that will be the worst case scenario. Okay, that is why this number is very important for you. So you will have to look at this number with more importance. But if you look at accuracy, it gives equal importance to both true positive and true negative, which is kind of not good, because it will give equal importance to both. So we have another parameter called sensitivity or recall, which only gives importance to true positive. It does not look at true negative at all. Okay, so sensitivity or recall will not look at true negative at all. So it doesn't care how well you predict a non-cancer patient, how well you identify a non-cancer patient. It will only look at whether you are identifying an actual cancer patient or not. If you are identifying an actual cancer patient, that means you are good. It will not look at whether you are identifying a non-cancer patient or not. So it only looks at the true positives. So how, out of all actual cancer patients, how many cancer patients did you identify? That is what sensitivity measures. And this is of most importance in such scenarios where it is a life and death situation. There you always look at parameter sensitivity. You do not look at accuracy. You look at sensitivity in that case. Okay, so this is what sensitivity measures. Is that clear, guys? Sorry guys, I was on mute. Yeah. So similar to sensitivity, we have another parameter called specificity, which only gives importance to true negative. Okay. This only gives importance to true negative. So the formula for that is this: true negative divided by this row total. Okay. It is the second row total now. And the interpretation is also similar. Out of all actual no, out of all actual no, how many no did you identify, or how many no did you predict? This is a case of specificity. This is another parameter which measures how well are you identifying your no. Sensitivity measures how well are you identifying the yeses in data. This measures how well you are identifying the no's in your data. Okay. So depending on which one is more important to you, is identifying yes more important to you, or is identifying no more important to you, you measure the parameter. You either measure sensitivity or you measure specificity. Most usually you measure sensitivity. I have never seen places where you measure specificity also, but most usually you measure sensitivity. Okay. So the interpretation is similar. Instead of actual ones, you write actual zeros, and instead of predicted ones, you write predicted zeros, because this is measuring zeros. Okay, this is your predicted zero, this is your actual zero. Okay, guys. Now let us go back to the same example that we were discussing and try to find these two parameters. So can somebody tell me now what is sensitivity here? If you remember the formula, can you tell me what is sensitivity now? This is the true positive rate. Okay, so I'll take this 2, which is the true positive value. So this 2 divided by the row total. So 2 plus 2, 4, right? So again, this is also 50%. So I took a very bad, so luckily or unluckily or by coincidence, it turned out to be 2 everywhere. So everywhere we are getting 50%. Okay, so this is sensitivity. Similarly, what will be the formula for specificity? This will be this particular 2, this 2 divided by 2 plus 2. So this also is 50%. Okay, because we had 2 everywhere, every number is coming as 50%, but it may not be the scenario. Okay, so in this case, in specificity, I have taken this 2 divided by this total. Okay, now you understand why it is called confusion matrix, right? Because we have a lot of parameters like this. Okay, now you let me give you another example which will help you understand why is sensitivity so important, why you cannot just rely on accuracy and go ahead. So let us take a scenario where you have 95 zeros in your data and you have 5 ones in your data. This is the actual value. Okay, this is the actual value, and let's say you have predicted all 100 as zeros. You have predicted all 100 as zeros. So let me say these are actual cancer cases. Okay, so you have received 100 patients. Out of that, 95 do not have cancer, and 5 of them they have cancer. Okay, 5 of them they have cancer, 95 do not have cancer, and you predicted that all 100 are zeros, or all hundreds do not have cancer. Is this good or is this bad? Is this prediction good or is this bad? Why is this bad, Anupama? Why is this bad? Bharati says it is good. Others are saying it is bad. Why it is bad, or why is it good? What do you think? Yes, it is bad because 5 of them are in danger. Yes, so that is why it is bad. Yes, exactly. Okay, so it is bad. It is a very bad model because 5 patients have cancer and you're not even identifying them. So what's the point? What's the point of you being a hospital if you're not able to identify the cancer patients? But let us calculate, let us draw the confusion matrix for it. Okay, let us draw the confusion matrix. This is actual, this is predicted. Okay, so let me write 1 and 0 here. So instead of yes and no, I'm writing 1 and 0. So what will be this number, guys? Can you tell me? What will be this number for this case? Yes, it will be 0 because I am not identifying even one cancer patient. So it will be 0. What will be this number? What will be this number? 0, 5, 5. Yes, this will be 5. This will be 5 because there are 5 actual ones, but I am saying 0. I am saying 0 to everybody. But out of that, 5 are actually ones. So this will be 5. What will be this number? 95. So are you predicting 95 ones? Sijo, look at the column. The column is 1. It is 0. You are predicting 0 1. So it will always be 0. And this one will be, obviously this will be 95 because the total has to be 100. Right? So this is what you get as the confusion matrix. Now let me write down the names of these. What is this? This is true positive. This is false negative. This is false positive. And this is true negative, right? Now let me calculate the accuracy. Now all of you agreed that this model is a waste model, right? Because it is not able to identify even 5 ones. So this model is useless. And we said this based on the business. We are not even looking at analytics here. We are just looking at the business scenario that I have 5 cancer patients out of 100 and I have to identify them. I have to somehow identify the 5 cancer patients. And my model does not identify even one of them. So it's a very bad model. It's a useless model basically. So this I understand from the business. I have nothing to do with analytics. I just understand this from business. Now let us use analytics and find the accuracy. Okay, let us find the accuracy. So the accuracy is true positive plus true negative divided by total. So what is my true positive value? It is 0. So I'll write 0 plus true negative is 95. So I'll write 95 divided by total, which is 100. So I get an accuracy of 95%. Is this bad now? Is the accuracy bad? No, the accuracy is good. But we understood from the business that it is a useless model. So that is where the conflict arises. This is where conflict arises between the business understanding and what you get from analytics. So what is the takeaway here? The takeaway here is that you should not look at just accuracy, because here accuracy is giving equal importance to true positive and true negative, but the situation, the scenario, the business case requires you to not look at true negative at all, because this is not important for us. The most important thing for a cancer hospital or diagnosis center is to identify true positive. This does not matter at all. So you should not look at accuracy in such scenario. Okay, you should only look at sensitivity. That is why we saw sensitivity. What was sensitivity? It just looks at true positive. It does not look at this number at all. So we should look at sensitivity in such scenarios. Now let us calculate sensitivity. What is the formula? It is true positive divided by row total. So true positive plus false negative, right? So what would this number be? It will be a big 0. So now you understand that for sensitivity we are getting a 0%. So we should have looked at sensitivity in this case and not accuracy. If you looked at accuracy, you would have believed that your model is a very good model, which is giving you 95% accuracy, but it is a useless model. So sensitivity will tell you that it is a useless model because sensitivity is 0. Accuracy will not give you that picture. So it is very important to see which parameter to look at under what business scenario. Okay? You cannot just blindly look at accuracy or sensitivity. You should look at both. And based on the scenario, you should give importance to one of them or both of them or whatever. Okay? So did you get the point, guys? Yes, that is correct, Anupama. Okay? Now let me give you another scenario. Let me give you another scenario. Now we saw that this model was useless, right? Because it predicted all 100 zeros, right? So it was a useless model. So just pay attention for another 5 minutes before we take a break. No, that's what, Arpita. I have never found such a scenario. Okay, I have never found such a scenario where specificity is important. So that is why I'm not discussing that. Okay, so let me change this. So we just found that this model was a useless model. So let me change the model. So now what I will do, I will predict all 100 as ones. Okay, all have cancer. Now, do you think this is a good model? Don't think from an analytics perspective, think from a business perspective. Think from a business perspective, will a hospital which says everybody who comes to the hospital has cancer, will that be good? No, no, right? Definitely that will not be good. A hospital which always tells that whichever patient is coming to it has cancer, that will obviously be a very bad hospital, right? Now let us calculate the confusion matrix for such a hospital or for such a scenario. Let us do that. So I will write actual, I will write predicted 1 and 0, actual 1 and 0. Now tell me these numbers, guys. What will be this number? What will be this number? 100? Are you sure? 95? Are you sure? So 95 have actual cancer. So look at this row and this column also. How many of them have actual cancer? 95? No. 95 did not have actual cancer, right? Only 5 had actual cancer. So this number should be 5. Right? This number should be 5. What is this number? So you are not predicting any 0. You are predicting all ones. So this number will be 0 and this number will be 0. I can write 0 for this entire column because I am not predicting any 0 at all. I am predicting all ones. Right? And this number is 5. What is this number? Obviously it will be 95 because there are 95 zeros, but I have predicted 1. So this number will be 95. Okay. Now let us calculate all the parameters. Let us calculate all the parameters. What is the accuracy? Yes, guys, what is the accuracy? 5%, okay, 5%. What is the sensitivity? What is the sensitivity now? 5 divided by 100. What is the formula for sensitivity, Bharti? It is 100%. 5 divided by 5 plus 0. Not 0%, it is 100%. It is 5 divided by this row total. So 5 by 5, which is 100%. We just saw that in such scenario we should look at sensitivity. But if I change the scenario a little bit, my sensitivity is becoming 100%. So once again we have a clash. We have a clash between business understanding and between what analytics is giving us. Right? We have a clash once again. So how do we resolve it? So previously we saw that we should not look at accuracy, and now we are looking at a scenario where if we look at sensitivity, once again we are going wrong. If you just look at sensitivity here, you will think that this is a very good model, but this model, again we discussed, it is a useless model because a hospital cannot say everybody has cancer. So this is a very bad model, but we are getting a sensitivity of 100% here. So what is the conclusion then? But the previous scenario told us that do not look at accuracy because you might be deceived looking at accuracy. So is the conclusion that both parameters are important? As Bharti has mentioned, that we should look at both of them together? No, there is still another parameter which I will talk now. There is still another parameter called precision. Okay. So you guys are partially right that of course we should look at both accuracy and sensitivity, but there is still another parameter called precision which we will use to prevent conditions like this. That so that the hospital does not start predicting everybody as one. To put that into check, to have a constraint on that, we have another parameter called precision. Okay, and the formula for that is true positive divided by, this time the column total, this time not the row total but the column total. Okay, so false negative plus true negative, this time the column total, sorry, this one, this column total, this one, true positive divided by true positive plus false positive. Okay, so the interpretation of this is that, so what is the denominator here? What is the denominator here? Yes guys, what is the denominator here? All predicted, yes. All predicted, yes. Yes. So out of all predicted yes, how many are actual yes? Okay, this is the interpretation of precision. So this will put a check on whether you are predicting unnecessarily yes, or whatever you are predicting are actually a yes. This will put a check on that so that you are not able to predict everybody as yes. So let us calculate the precision in this case. Let us calculate the precision. What will that be? So it will be 5 divided by 100, and it will be only 5%. It will be only 5%. So precision will tell you that whatever you are predicting is not good, because if you predict 100 patients have cancer, only 5 of them actually will have cancer. So this will tell you that your model is flawed. So the ideal answer would be that both sensitivity and precision should be high. Both of them, not just one of them. Both of them should be high, not just one of them. Okay. So using both sensitivity and precision, you will be able to say whether your model is good or whether your model is not good. Okay. If you just look at sensitivity, you may go wrong in scenarios where you are predicting all ones. Okay. If you don't look at sensitivity, see, if you look at accuracy, obviously that is bad. We saw in this case we got an accuracy of 95%, but actually this model was useless because it was not identifying even one cancer patient. Okay. Okay, so this is how you alter your parameters, and based on the scenario that you have at hand, and you try to evaluate your model by looking at accuracy, or by looking at sensitivity, or by looking at precision. Okay, so these are the four parameters that we have. So what did we see? We saw accuracy. The flaw in accuracy is that it just looks at true positive and true negative. Okay, and it gives equal importance to both of them. Then we saw we have sensitivity, which only looks at true positive. So this is very helpful when you want to identify cancer patients, for example. Then we saw another, but this also has a flaw that if you predict all ones, true positive, this sensitivity will become 100%. If you predict all ones, sensitivity will become 100%, and you cannot predict all ones. That is also not a good model where you predict everybody has cancer. So to put a check on that, we have another parameter called precision. Okay, this will put a check on such cases where you are predicting all ones. Okay, so precision will be true positive divided by column total, not row total. Everywhere else you have row total, here you will have column total. And then of course we have another parameter called specificity. Okay, specificity, it looks at true negative only. Just like sensitivity looks at true positive only, specificity looks at true negative only. Okay, any doubts guys so far? No, there is no flaw for precision. But precision alone will not give you a clear picture. You have to use precision along with sensitivity. Okay, so remember the interpretation for these parameters, guys. So watch the recording of this class many times if you have to, but try to understand the interpretation. But this is not just for logistic, but for all classification algorithm. Okay, so we will see this multiple times. So every now and then we'll be talking about these parameters. Okay, so you will anyways remember these parameters because this is not a one class topic. This will come again and again in almost every classes. Okay, so I will share a few exercises on whatever we have just covered. I will share a few exercises by tonight. So by tonight I will have one more module here which will talk about, so it will have the video of today's class, and it will have several examples which will help you practice. Okay, so I will not give you examples which will require use of Python because we haven't seen Python for logistic regression yet, and we haven't seen logistic regression yet. Okay, so logistic regression we are yet to cover. We have just seen how do we evaluate a classification algorithm. Harsh, which algorithm has 5% fault? This does not have 5% fault. It doesn't make business sense. That is important. 5% fault, 10% fault doesn't matter. The model should make business sense. And that's what we were discussing. If your model cannot identify even 5% or even one cancer patient out of 5, it's a waste model. It's a useless model. Because out of 100 cancer patients, out of 100 visitors to a hospital, 5 of them have cancer. Okay, 95 do not have cancer. And if you are not able to identify even one out of those actual 5s, it's useless. So it doesn't make any business sense. It's not about the number. The first and the foremost thing is it should make business sense. If it doesn't make business sense, even if you show 100% accuracy, it's useless actually. Okay, so it should make business sense. That is why you will not look at the number there. You will look at the interpretation, which is why I say the interpretation of these parameters is very important. Okay, is it clear, Harsh? So any other doubts, guys? Yes, every model has a fault because no model is perfect. No model will give you 100% accuracy. We have seen in case of regression also, right? You'll always have some error. We try to minimize that error, but you cannot avoid errors because every model will have some error or the other. We try to minimize the error and we try to look for a model which makes more business sense. And that is why you can say analytics is difficult, because if it was so easy that you just apply one model and it is done, then there wouldn't be so much craze, right? Everybody would have become a master of analytics, but not all people are, because it is difficult. You have to understand every algorithm. You have to understand the good part of every algorithm, the advantage and disadvantage of every algorithm. You have to understand the maths behind every algorithm, the interpretation of every parameter, because these formulas you can easily get on Google, but directly using these formulas you will never be able to make sense out of it unless you know the interpretation. So it is important to know the interpretation. Okay, only then you will know where to apply which parameter. Otherwise you will be just copy pasting codes from Google and not knowing which one is important, which one is not important.